Hello everyone. Chemistry Made Easy is aimed at explaining chemistry concepts in simpler way. Here, every topic will be taught in detail with examples so that the viewers will be able to understand the concepts clearly. In today's video, a detailed introduction to isolable analogy along with some essential concepts will be explained. Coming to isolable analogy, it's a very interesting topic as it is considered as a bridge between the activity of organic and inorganic molecules. The isolability concept is used to predict the stability of organic and inorganic compounds. So this is useful in synthesizing of new compounds, clubbing the organic and inorganic molecular fragments. It is used to relate the structures of organic, inorganic and organometallic fragments to predict their bonding properties. Coming to the isolable analogy, it was first described by a person by name Rolf Hoffmann, who is a Polish American chemist, who also won the Nobel Prize for the same in 1981. He developed the concept of isolable analogy or principle to show the connection between two prominent areas of chemistry, which is organic and inorganic chemistry. The isolable analogy term has been adopted from the Greek words isos meaning similar and lobos meaning lobe. So isolable means similar lobes. Rodolphe Hoffmann, in his Nobel speech, he defined isolability as a molecular fragments are isolable if the number, symmetry, properties, approximate energy, the shape of the frontier orbitals, and the number of electrons in them are similar. That is, he stressed similarity and not identical. According to the concept of isolable analogy, the molecular fragments of a cluster are supposed to be isolable or tagged to be isolable if they satisfy certain criteria. That is, if they possess same number of frontier molecular orbitals. What are these frontier molecular orbitals? We'll be learning in the coming slides. So, according to the concept, in order for two molecular fragments to be isolable, their frontier molecular orbitals should have similar shape, similar symmetry, and radial extent, should have approximately the same energy, and should have same number of electrons for cluster bonding available for forming a bond between each other. So the isolable fragments may not be isostructural and isoelectronic. They should only possess similar characteristics for the frontier molecular orbitals. So the whole molecular fragment may not be similar, may not have same structure or may not have same exact number of electrons. But the frontier molecular orbitals which are used for bonding with each other should have same energy, or that is similar energy or same number of electrons. When molecular fragments are isolable, then they can likely be combined to form stable molecules. So we use this isolable analogy as to predict whether the two fragments what we have can form a stable molecule when clubbed together. Thus, isolable fragments are considered to be compatible building blocks for construction of stable molecules. So, the concept of this isolable analogy will help us to predict about the stability of the bond forms or when the stable bond is formed. According to the concept, it is seen that when two molecular fragments are isolable, then they are likely to form stable bonds between them and the resulting molecule would be stable. The symbol used for isolability or isolable analogy is as shown here in red. It's a double-headed arrow with a loop in the center. So one thing what you have to remember from this slide is, in order for two molecular fragments to be considered isolable, then their frontier molecular orbitals respectively should have similar shape, similar symmetry and radial extent, similar energy and same number of electrons for bonding. That is, the number of valence electrons should be same. As I mentioned before, we'll see what are these frontier orbitals. According to IUPAC Gold Book, frontier orbitals are nothing but the highest energy occupied molecular orbital, HOMO, which are filled or partially filled, and lowest energy unoccupied molecular orbital, LUMO, which is completely or partially vacant. So, in a simpler way, frontier orbitals are the one which are at the frontier, which are at the top, or which are open to the others, which are between occupied and unoccupied. So these orbital, the frontier molecular orbitals, are the prime determinants, are the prime factors for their chemical, optical and electronic properties. They are the one which result in these properties of the molecules. Now coming to the concept of isolability, here onwards we will see how to check the molecules if or the molecular fragments are isolable to each other, or how to know or how to make them isolable to each other. That is how to construct the molecular fragments. As I said before, when two fragments have the same number of valence electrons, they are considered as isolable. Again stressing on the point, the two fragments should have same number of valence electrons. Okay, as I said, molecular fragments are considered to be isolable if they have similar symmetry property, approximate energy, similar shape and similar or same number of electrons. These are the four criteria which has to be satisfied by the frontier molecular orbitals of the molecular fragments which are considered to be isolable or in order to be isolable. Let's take few examples. In the examples what will be taken from now onwards, we will be considering both organic molecular fragment and inorganic molecular fragment and also some metal complexes. Now, how to get a molecular fragment is by removing a easily removable entity, leaving group. For example, from methane, if I start from methane, we can get a methyl methyl molecular fragment by removing the hydrogen. So here what I get the methyl fragment and a hydrogen ion. So methyl radical and the hydrogen radical, both of them having one electron each in their respective frontier molecular orbitals. You can simply imagine a methane from which you are removing the hydrogen. So hydrogen comes out with its one electron which was shared before, and carbon with the remaining three hydrogen will come out of from hydrogen with one molecular orbital and an electron which was shared with that leaving hydrogen atom. So as a result you get a methyl radical and a hydrogen radical. Now if I look at this methyl radical, the number of valence electrons will be calculated as follows. Hydrogen, you know there is one valence electron and there are three hydrogen atoms in methyl radical. So totally 3. Carbon belongs to group 6 with the number of valence electrons being 4. So totally there are 7 valence electrons. Right? So this methyl radical has 7 valence electrons and one frontier molecular orbital with 1 electron in it. Remember, only when the electron is present, a molecular orbital will exist. Now, if I take the example of this NH2, amine radical. So, amine radical is formed by the removal of one hydrogen atom from ammonia molecule. So, as I explained for methane here, same thing is applicable here also. When you remove an hydrogen atom from ammonia, the hydrogen will come out by taking its electron which was shared with NH2 and the electron. That is the molecular orbital of hydrogen along with an electron will come out. Now what will be left out is that molecular orbital of the ammonia which was shared with the hydrogen orbital and an electron in it. So coming to the number of valence electrons in it, there are two hydrogen atoms, so there are two valence electrons, and nitrogen belongs to the 7th group with 5 valence electrons in it, totally 7. If you look at these two molecular fragments which are obtained by removal of hydrogen from ammonia and hydrogen from methane. So remember, when you remove one atom from a molecule, you result or you end up getting one empty orbital with an electron in it. So partially filled orbital, which we consider to be a frontier molecular orbital. So these two fragments, they have one frontier molecular orbital each with one electron, and the number of valence electrons are equal, 7. So accordingly, because they have similar shape of frontier molecular orbitals, similar energy of frontier molecular orbitals, and similar symmetry property, we can club these two molecular fragments to get stable molecules, and the result is as seen here. You can get methylamine by clubbing methyl radical and amine radical, and ethane by clubbing two methyl radicals, and hydrazine by clubbing two amine radicals. So this is how we can use the isolobal analogy concept in forming these stable molecules, or in arriving at whether the molecule formed from these molecular fragments are stable or not. We'll go further. In the previous slide, I had took an example where we took methane, removed one hydrogen. Now, if you remove other hydrogen atom, the second hydrogen atom, you end up getting a methine radical with two frontier molecular orbitals with one electron in each. So the total number of valence electrons in this radical molecular fragment or radical will be 6 valence electrons. Remember, when you remove two hydrogen, it like you will be creating two vacant orbitals. Similarly, from ammonia, if you remove two hydrogen, you are creating two vacant orbitals with one electron in each. Because the leaving group will take, or leaving atom will take its part of the electron. So even this has 6 valence electrons. So these two can also be considered as isolable to each other. And if that's the case, they should be forming stable molecules. And as it is, they can be clubbed to form methylene amine. And if I club two methine radicals, I get ethene. Because there are two orbitals with two electrons each, they form, and they are perpendicular, they will form a pi bond. Going to other examples. If I consider this methine radical with two frontier molecular orbitals with one electron in each, which is already explained that it is isolable with NH radical, it is seen that even oxygen with 6 electrons in it is also, valence electrons in it, is also found to be isolable with these two molecular fragments. Similarly, if I remove the third hydrogen from methane, I end up getting a CH molecular fragment with 5 valence electrons and 3 frontier molecular orbitals with 1 electron in each, which is found to be isolable with this nitrogen radical, not atom, nitrogen radical with 3 electrons in 3 orbitals, frontier molecular orbitals, totally having 5 valence electrons. So these two can club because they are found to be isolable with each other. That is, each of them have 3 frontier molecular orbitals with 3 electrons in them with similar shape and similar energy. They can club to form a stable molecule, which is hydrogen cyanide. Similarly, it is seen that the CH fragment is also found to be isolable with phosphorus radical with 3 frontier molecular orbitals with 1 electron in each and a total of 5 valence electrons. Like this, we can find out the different isolable species by checking the number of orbitals they have, frontier orbitals they have, and the number of electrons present in them. As I told you, we'll see how we arrive at the construction of isolable fragments. So for example, if I take methane, how to arrive at the molecular fragments from methane. In order to generate isolable fragments, the molecule should follow certain criteria, like it should satisfy octet rule, and all bonding and non-bonding molecular orbitals should be filled, and all antibonding molecular orbitals should be empty. These are the two criteria which has to be followed for a molecule in order to generate an isolable fragment. So if I start from methane, after removal of hydrogen atom, it generates a methyl radical. This methane and the methyl radical will retain their molecular geometry, as the frontier orbitals will always be directing in the direction of the missing hydrogen, that is from where the hydrogen atom has been removed. Further removal of hydrogen atom results in the formation of second frontier orbital following the same criteria. This process repeats until only the one bond remains to the molecular central atom like CH. If you look into this example here, so the frontier molecular orbitals are pointing out in the direction where the hydrogen atom has been removed. So this was about how we can construct the molecular fragments starting from a stable molecule like from methane to CH radical. We'll extend the same concept to the transition metal complexes and see if there are any metal complexes which are isolable to methane or the methyl radicals. In the way the octet rule has been used or found to be a criteria for the p block elements to get isolable fragments from them. Similarly, here 18 electron rule is applicable for transition metal complexes. Okay, the 18 electron rule has to be followed by them in order to get a stable isolable fragments from the transition metal complexes in order for them for us to predict their reactivity towards the main group elements or main group molecular fragments. So the concept remains the same. The number of frontier molecular orbitals and the number of electrons in them is found to be 18 minus the valence electrons. Okay. Now as I mentioned here, the number of frontier orbitals will be equal to number of electrons in those orbitals, that is 18 minus valence electrons. We'll take the example of a simple carbonyl compound, pentacarbonyl manganese, that is MnCO5. So how to calculate the valence electrons in such complexes? We have to add the number of valence electrons in the metal manganese and the number of electrons donated by carbonyl ligand. Remember, carbonyl ligand donates 2 electrons each. So manganese has atomic number 25 and its electronic configuration is outer shell electronic configuration being 3d54s2. So totally 7 valence electrons. Plus the number of electrons donated by the ligand will be 5 multiplied by 2, 10. So it will be totally 17 valence electrons in this particular complex MnCO5. So as I told you before, following this equation, number of frontier orbitals will be 18 minus valence electrons. So I get one frontier orbital with 1 electron. So when I get the value 1, it means there is one frontier orbital with 1 valence electron. Right? Remember, MnCO5 is not a monomer, it is a dimer. It exists as Mn2CO10. So initially MnCO5 doesn't exist. I am breaking that Mn2CO10 into MnCO5. When I separate those two fragments, what I get? I get 2 MnCO5 separated with one frontier molecular orbital with 1 electron in each of them. That's what it is. This is a MnCO5 fragment with 1 frontier molecular orbital and an electron. If you look at this condition, look at this structure, what I can relate it? I can relate it to the CH3 fragment containing 1 frontier molecular orbital with 1 electron. So as I told you, here we are considering the number of electrons in the frontier molecular orbital should be same and the frontier molecular orbital symmetry energy should be same and number of frontier molecular orbitals should be same or similar in order for them to be considered to be isolable. So all these criteria are satisfied by these two fragments. They have 1 frontier molecular orbital each, 1 electron in them each, and the number of valence electrons here it is 7 and it is 17. So irrespective whether it is 17 valence electrons or 7 valence electrons, there are 1 each frontier molecular orbital with 1 electron in them. That is sufficient for them to be considered to be isolable to each other. We'll see some more examples to understand the concept clearly. So like how we generated the molecular fragments from methane by removing hydrogen at each step. Similarly, in transmetal complexes, the fragments are generated by removing the ligands at each step. So, a 18 electron transmetal complex is isolable with methane, as removal of ligand is equal to removal of hydrogen of the methane group, right? The metal center in MLX initially when you begin the process should be D6 metal. When you remove a ligand, what happens? You get a Ml5 minus fragment. That is, there will be a negative charge. You know that according to 18 electron rule, the formed complex should be neutral charge or zero charge criteria is one of the essential criteria. So in order to get or convert a negatively charged molecular fragment to a zero charge fragment, you have to just simply increase the positive charge. That is, you take or replace a D6 metal with the D7 metal. So initially when you have a MOL6 example, molybdenum complex, you remove a ligand, you get MOL5 minus. You replace this molybdenum which is a D6 metal to manganese which is a D7 metal. So what is happening here? You are maintaining the zero charge criteria. At the same time, in order for these transmetal complexes to be considered, they should satisfy the 18 electron rule and have zero charge, and their ligand should be 2 electron donors. Essential. That is their Lewis bases. Ligands are Lewis bases. Let's see. If you take the example of molybdenum hexacarbonyl complex, it is a 18 electron valence electron containing complex. It is isolable with methane, which is 8 valence electron. So here, what relationship we can develop? 18 valence electron complex is isolable with 8. So 10 minus valence electron of the methane part. Similarly, the pentacarbonyl manganese, which is a 17 valence electron complex, is isolable with methyl radical, which has 1 frontier molecular orbitals each with 1 electrons in them. So, likewise, if I am removing the next another carbonyl from this, what I get? I get MnCO4 minus. To maintain the zero charge criteria, I'll replace manganese with iron. Iron is a D8 metal. So then I'll get 16 valence electron complex which is found to be isolable with CH2 radical which have 2 frontier molecular orbitals with 2 electrons in them. And likewise, if I remove one more carbonyl ligand from this fragment, I end up getting FeCO3 minus. So I replace iron with the next group metal, cobalt. So which is a D9 metal. So I end up getting a neutral or a zero charged 15 valence electron complex which has 3 frontier molecular orbitals and 1 electron in each. So it is found to be isolable with CH radical. So here what you have to understand is, initially if I take FeCO5, it may not be isolable with methane, right? So what is to be considered is, when you have a molecular fragment, you have to focus completely on the frontier molecular orbitals. How many frontier molecular orbitals are there? So one frontier molecular orbital will have 1 electron. So check another molecular fragment which have the same number of frontier orbitals and number of electrons same. They are found to be isolable with each other. Simple. We'll extend the same concept what we had used in 18 valence electron containing complexes to 16 valence electron containing complexes. Only changes in the formula. So here the number of frontier molecular orbitals will be equal to the number of electrons in those orbitals, that is 16 minus valence electrons. For example, if I take a FeL4, a tetrahedral FeL4 complex, L can be any ligand which is a 2 electron donor. Now for example, the valence electrons in iron is found to be 8 plus the number of electrons donated by the ligand will be 8. 2 multiplied by 4. So totally 16 valence electron complex. See, in this complex, there are no frontier orbitals because you have not removed any ligand yet. So that will be isolable with methane because even there I have not removed any hydrogen yet. So if I remove a ligand, what happens? I will have a complex which will be FeL3 minus. To maintain the zero charge criteria, I'll replace iron with the next group metal which is cobalt. So the 16 valence electron complex becomes 15 valence electron complex. So here what is happening? After removing the ligand, I'll get one vacant frontier molecular orbital with an electron in it. So that would consider to be isolable with methyl radical because even that radical has one frontier orbital with one electron. Similarly, if I remove one ligand from this COL3 radical, I end up getting NiL COL2 minus. To maintain the zero charge criteria, cobalt will be replaced by nickel. So what happens? I get a molecular fragment containing two frontier molecular orbitals with one electron in each, which is found to be isolable with CH2 radical, which also has two frontier molecular orbitals with one electron in each. Similarly, now if I remove one more ligand from it, I end up getting NiL minus. So to maintain the zero charge again, I'll replace nickel with the next group which is copper. So what happens, because I have removed an electron there, removed an ligand there, I will be getting three frontier orbitals with one electron in each. So this is found to be isolable with CH. Even that has three frontier molecular orbitals with one electron in each. Again, I am stressing on the point, whenever you are trying to find out the isolable fragments, check how many molecular orbitals, frontier molecular orbitals are there, and check the number of electrons in them. So that will give you the isolable fragments, or will help you to find out the isolable fragments. So this was about how to construct the molecular orbitals from carbon or p block elements, that is the main group elements, uh, complexes, or from transition metal complexes with 18 electrons and 16 electrons. Now, for p block elements, except for boron, all other p block elements contribute 8 electrons for the metal bond, that is the cluster bonding. Because boron group is electron deficient, that is an exception. So for example, in case of p block elements, number of frontier orbitals will be number of electrons in these orbitals, that is equal to 8 minus valence electrons. Example, in CH3, number of frontier orbitals will be 8 minus valence electrons here is 7. Right, 4 plus 3. So it is 1. So this fragment has one frontier orbital with one electron. Tin, R2, R can be any group which is a one electron donor species. So number of frontier orbitals, again here it will be equal to 8 minus 6 because tin belongs to carbon family. So totally you get 2. So SnR2 will have 2 frontier orbitals with 2 electrons in it, that is 1 each. But for boron group, number of frontier orbitals will be equal to 6 minus valence electron. This is very important. Whenever, for example, if I take BH, here number of frontier orbitals will be 6 minus 4, that is 2. So there will be 2 frontier orbitals with 2 electrons in it. So when you get 2, it means 2 frontier orbitals with 2 electrons. If you get 1, 1 frontier orbital with 1 electron in each of the orbitals. It means because BH has 2 frontier orbitals with 1 electron in each, which is that moiety in the carbon molecular fragment which has 2 frontier orbitals, it's CH2. So CH2 also have 2 frontier orbitals with 1 electron in each, and SnR2 also have 2 frontier orbitals with 1 electron in each. All these three are found to be isolable with each other. So this was it all, where I've tried to explain the introductory of the isolobal analogy and also how to arrive at the construction of molecular fragments and to check whether they are isolable with each other. Please remember, in order for two molecular fragments to be isolable with each other, they should have same number of frontier molecular orbitals with same number of electrons in them. Until now, we have not gone to the molecular orbital concept yet. So, need not worry about the symmetry and shape and all. Only what you have to understand is check the number of frontier molecular orbitals obtained in the fragments and then compare with the fragments with whose isolability you have to verify. If they have same number of frontier molecular orbitals, then they are isolable with each other. Thank you. So in the next lecture, I'll be explaining about the molecular orbital concept behind the isolobal analogy, and we will also solve certain problems related to isolobal analogy and how it could be an aid in synthesizing different new compounds.